Chapter 4 is on chemical reactions. Chemical reactions involve the formation of a new substance with a different composition and properties than the initial substance. These reactions involve the rearrangement and exchange of atoms to produce new molecules. For example, octane is a component in gasoline that you would put in your auto engine. It combines with oxygen and undergoes a combustion reaction, forming carbon dioxide and water. The carbon dioxide and water are called the products, what we created. The octane and oxygen are called the reactants, what we started with. The products, carbon dioxide and water, have different properties than the reactants, octane and oxygen. So we can see we created new compounds by seeing how the atoms rearranged and also by how they behave. This is a list of physical evidence that indicates a chemical reaction has occurred. If I had two substances and I mix them together and the color changed, that is an observation that indicates a chemical reaction has occurred. In this flask, I have sodium hydroxide. I added a substance called phenolphthalein, which is a clear solution. Sodium hydroxide is a clear solution. When I mix them together, I get this hot pink color. This indicates I created a new substance because it has a different physical property than sodium hydroxide or phenolphthalein. The next one is if I were to mix two solutions together and I formed a solid, that is another indication that I had a chemical reaction occurred. For example, in this test tube, we had two clear liquids that we mixed together and we see this white cloudy substance. If we let this sit, this will settle at the bottom and form a solid material. So this indicates that a chemical reaction has occurred. If I have two liquids and I mix them together and I see bubbles forming, this indicates I formed a gas. For example, if I have Alka-Seltzer tablets and I put them into a beaker of water, we see the creation of bubbles. And that tells us again we have a gas. So we created something with a different physical property than what we started with. Evolution or absorption of heat also tells us a chemical reaction has occurred. So for example, cold packs would be the example of absorption of heat. In a cold pack, you have two substances or compounds. When you crack your cold pack, you're mixing those substances together and you're absorbing heat. It gets cold, so you can apply that to your inflamed area, wherever you may have had an injury occurred. Evolution of heat would be an example of a hot pack. So when I go skiing and it's cold, sometimes I like to take a hot pack, I break it in half, and I'm reacting to chemicals that are giving off heat. Emission of light is another observation that you might see that indicates a chemical reaction occurred. For example, glow sticks. Glow sticks do not glow until you crack them. When you physically crack that plastic, you are mixing two chemicals together that give off light. So this indicates a chemical reaction has occurred. Elephant's toothpaste is a nickname given to the combination of H2O2, hydrogen peroxide, NaI, sodium iodide, and liquid dishwashing soap. Is this a chemical reaction based on your observations? Hydrogen peroxide, sodium iodide, and soap are all clear liquids. When you mix those three together, you produce what's shown in the picture here. So what we're seeing here is you can see we changed color. We were clear and we went to I'd say this is a light blue color. Also, they were clear liquids, and that kind of the volume increased, and there's bubbles in it. So you observe bubbles in that liquid. And you can't really see in this picture, but you often see steam coming off the top, which indicates you have the production of heat. And if you have your hand near that, you would feel the warmth. So now, based on your observations, would you say this is a chemical reaction? I would say yes, based on what we just learned. There are some terms to be familiar when you're writing chemical equations. The first are the reactants. The reactants are the elements or the compounds that you are mixing together that you start with. Sort of like if you're baking a cake, that would be your flour, your sugar, your eggs, what you use to mix together, your ingredients. This triangle over the arrow means heat. For some reactions, heat is required to make the reaction go forward. What you create are called the products. So in this example, our reactants are carbon and oxygen. Our product is carbon dioxide. What's written in the parentheses tells you the physical state of your reactant and your products. So G stands for gas. S stands for solid. So carbon is a solid. Oxygen and carbon dioxide are gases. The other physical state you need to know is L is for liquid, and then AQ is aqueous, which means something is mixed in water. So that would be a mixture. This slide shows the states of your reactants and products in chemical equations. You can have a gas, liquid, or solid, or aqueous with their abbreviations. We are going to learn how to balance chemical equations. Let's start with a review on the law of conservation of matter. The law of conservation of matter states that atoms can neither be created or destroyed. Those atoms can only be rearranged to create new compounds. An equation must have the same number of and kind of atoms on both sides of the equation. For example, we have carbon plus oxygen forming carbon dioxide. We can see on the left in our reactants, we have one atom of carbon, and we have 2 atoms of oxygen. In our product, CO2, we have 1 carbon atom and we have 2 oxygen atoms. So we can check to see if our chemical equation is balanced. We can count again on the left. I'm going to check 1 carbon, 1 carbon. On the right, 2 oxygens, 2 oxygen. This chemical equation is already balanced. Some of them may not be, and we will be learning how to balance those that are not already balanced. A coefficient is a whole number that tells us the quantity of atoms or molecules. Coefficients are used to balance equations. Let's look at an everyday life example, making a grilled cheese sandwich. To make a grilled cheese sandwich requires 2 pieces of bread and 1 piece of cheese. I'm going to heat those up and produce 1 sandwich. So we're going to write this like a chemical reaction. So my bread is abbreviated as BR and my cheese is abbreviated as CH. I put this number 2 in the front of my BR. That is called a coefficient. It stands for the number of pieces of bread I have. And if I wanted to think of this as maybe atoms, I could say I have 2 atoms. I'm drawing as 2 white circles. And my cheese has nothing written in front of it. And if nothing's written in front of my element symbol, that implies it's 1. So that would be my one piece of cheese. And maybe I want to draw that at my atomic level as a black sphere. And when I combine them together and I add heat, I undergo my chemical reaction and I produced CHBr2. And drawing that at a molecular level, I still have one piece of cheese, and it is now combined with 2 atoms of Br attached to it. So this is showing me that I created a molecule from these different elements here, these different atoms. So this is showing us in CHBr2, there's no number written in the front. Again, it's implied 1, that I created one sandwich. So coefficient is the term to remember here. It's a whole number that's drawn, written in front of the molecular formula or of your element. Is this reaction balanced? This is the elephant toothpaste reaction we looked at earlier. The coefficients are the whole numbers written in front of the element or the compound's formula, and they tell us how many molecules we have of that specific compound. So the first one we have here is 3 H2O2s. This is the hydrogen peroxide. So this means we have 3 molecules of H2O2. The 2 indicates that we have 2 sodium iodides. And then here we have 2 sodium hydroxides. And there's nothing written in front of I2, so that just implies we have 1 iodine molecule. We have 2 water molecules. And nothing is written in front of the oxygen, so again, that implies we have 1 oxygen molecule. So we want to check to see if this reaction is balanced. So again, the law of conservation of matter says that we must have the same number of atoms of each element on the left-hand side of the arrow, where our reactants are, compared to all of the atoms of the elements on the right side, where our products are. So we're going to count up the number of atoms of each element. So in 3 molecules of water, we have a total here of 6 hydrogens. There's 3 of them, and they each have 2 hydrogens. We have 6 oxygens. We have, for 2 sodium iodines, 2 sodiums, and 2 iodines. For 2 sodium hydroxides, we have 2 sodiums, and we have 2 oxygens and 2 hydrogens. For I2, there are 2 iodines in 1 molecule. For our 2 water molecules, we have 4 hydrogens and 2 oxygens, and our 1 molecule of O2 has 2 oxygens. Now let's compare the left to the right. So let's start with 6 hydrogens on the left side of the arrow. On the right side of the arrow, I find 2 hydrogens in our 2 sodium hydroxides, and then 4 hydrogens in our 2 water molecules. And if we add that together, that gives us our 6 hydrogens. So that would be balanced, putting a check mark next to each of those. Now let's look at our oxygens. On the left, we have 6 oxygens. On the right, we have 2 oxygens in 2 sodium hydroxides, and then 2 oxygens in 2 waters, plus 2 oxygens in 1 molecule of O2. So if we add all those together, let's circle those in red so we can tell which is which. Here's our 6 oxygens, and we have 2 plus 2 plus 2 gives me 6 oxygens. So that one is balanced. Now our sodiums, we have 2 on the left and 2 on the right. So I circled those in green to show you that our sodiums are balanced. And then our iodine, we have 2 iodines on the left, 2 iodines on the right, so they are balanced. So we do have a balanced chemical reaction here. And we have coefficients in the front of the certain molecules in order to balance it. For us to balance the equation, we're going to learn how to insert coefficients if they are not already inserted. The law of conservation of matter says atoms can neither be created or destroyed. An equation must have the same number of and the same kind of atoms on both sides of the equation. So we're going to check that in this equation below to see if our atoms are balanced for the reactants with the products. So we're starting with hydrogen, H2. That tells us we have 2 hydrogen atoms. Oxygen indicates we have 2 oxygen atoms. And for H2O, we have 2 hydrogens and 1 oxygen. So we want to see if that is balanced. The hydrogens balance. Yes, 2 on each side. However, the oxygens, we have 2 on the left and 1 on the right. So this is an unbalanced equation, which means we'll have to be adding a coefficient in order to balance it. To balance an equation, you may need to add a coefficient. Or we can say we're going to change a coefficient of 1 that you don't need to write, it's implied, to a number other than 1. You will never want to change the subscript. So in the previous example, we were trying to create water. Hydrogen plus oxygen produces water. We said that was an unbalanced equation. So we'll need to add a coefficient. This is just to show you an example of what not to do. Never change the subscript. That would be easy. We said we didn't have enough oxygens. Our hydrogens were balanced. So we could just add a coefficient of 2 to our oxygen and water, and then we would have a balanced equation. 2 hydrogens on the left, 2 oxygens on the left, and 2 oxygens on the right. That would be balanced. But if we change the subscript, we change the compound completely. So water is something we can drink. It's necessary for life. Hydrogen peroxide is something in our medicine cabinet that's usually used to treat infections. You don't want to drink hydrogen peroxide, that will probably kill you. So it's very important, never ever change the subscript. To balance the formation of water, we need to add a coefficient. We determined it was not balanced because we didn't have enough oxygens in our water. And we can't add a subscript, so we can add a coefficient. So on the left, we have 2 oxygens, we have 1 on the right. So if we put a coefficient of 2 in front of our water, now we'll have 2 oxygens to balance 2 oxygens on the left and the right. However, when we do this, let's go ahead and take a count here. On the left, we said we had 2 oxygens. On the right, we have 2 oxygens because we have 2 waters and molecules. But what happens is we now have 2 water molecules, and that gives us now 4 hydrogens. A quick way that you can do this, instead of drawing your water molecules out, H2O and H2O, and seeing we have 2 hydrogens in each, we have a total of 4 hydrogens, you can multiply the coefficient by the subscript. So we can say 2 times 2 gives me 4 hydrogens, and 2 times 1 would give me the 2 oxygens. So when we add a 2 in front of the water, we have 4 hydrogens. Now on the left in our reactants, we have 2 hydrogens. So it's not balanced any longer, hydrogens. We need to add a 2 in front of hydrogen in order to balance this. So now we can count and say 2 times 2 of the subscript gives me 4 hydrogens. And this one, there's a 1, so 1 times 2 would give me 2 oxygen atoms. On the products for 2 water molecules, I have 4 hydrogens, 2 oxygens, and then I can check 4 hydrogens are balanced, 2 oxygens are balanced. Now we have a balanced Equation for the formation of water. The combustion of methane. Methane gas burns to produce carbon dioxide gas and gaseous water. Whenever something burns, it combines with oxygen. It's also called a combustion reaction. RXN stands for reaction. This is the chemical reaction. CH4 is methane. Physical state is G for gas. It's combining with oxygen, which implies it's burning, undergoing combustion. It will produce carbon dioxide gas and water gas. Let's see if this reaction is balanced. This picture down here represents a molecule of methane, or CH4. Here's a molecule of oxygen, and we're producing carbon dioxide gas and water. So let's determine if this is balanced. So in our molecule of CH4, we have 1 carbon and 4 hydrogens. 1 molecule of oxygen has 2 oxygen atoms. 1 molecule of CO2 has 1 carbon, 2 oxygen atoms. 1 molecule of water has 2 hydrogens and 1 oxygen. So we went ahead and combined on the products our 2 oxygens plus 1 oxygen to get 3 oxygens. And then let's compare the reactants to the products. So 1 carbon on the left, 1 carbon on the right is balanced. On the left we have 4 hydrogens, on the right we only have 2. So this is not balanced. And then on the left we have 2 oxygens and 3 oxygens on the right, so that one also is not balanced. So this is not a balanced reaction, so we will need to add coefficients. To balance the combustion of methane, we need to determine which element do we want to start with adding a coefficient to first. So there is a rule to follow, which is to start with an element that appears only once on each side of the arrow. So let's look at our elements in our reactants and our products. So carbon appears in CH4 in 1 reactant, and carbon appears in 1 product in CO2. Hydrogen appears in 1 reactant in CH4, and hydrogen appears in 1 product in H2. Oxygen appears in oxygen in 1 reactant. However, oxygen appears in carbon dioxide and in water. So oxygen is in 2 of the products. So don't start with oxygen in this example. So you could pick either carbon or hydrogen. It doesn't matter, but let's go ahead and we'll start with our carbons. So if we look at this reaction, on the left in CH4 we have 1 carbon. On the right in CO2 we have 1 carbon. So we don't have to write a 1 as a coefficient. Our carbons are already balanced. So let's go to hydrogen next, and we'll save oxygen for last. So hydrogen, on the left in CH4 we have 4 hydrogens. In the right in water we have 2 hydrogens. So in order to balance that, we're going to add a coefficient of 2 in the front. And so 2 times 2 would give me 4 hydrogens. So now our hydrogens are balanced. Now we'll go ahead and move on to oxygen. Now we know all the oxygen atoms on the right. We can calculate the number to go in front of the oxygen on the left. So let's look at our oxygens on the right. So in carbon dioxide, we have 1 carbon and we have 2 oxygens. We have, for 2 water molecules, we have 2 times 2, we said, is 4 hydrogens, and 2 times the oxygen gives me 2 oxygens. So now we have 2 oxygens plus 2 oxygens gives me a total of 4 oxygens. So the coefficient that's going to need to go in front of the O2 on the left is going to be 2. because 2 times 2 as the subscript gives me now 4 oxygens. And in CH4 we have 1 carbon and 4 hydrogens. So we can check that everything is balanced. The 1 carbon is balanced, the 4 hydrogens are balanced, and our 4 oxygens are balanced. The last rule for balancing equations says express the coefficient in lowest terms if necessary. What that would mean is sometimes to balance the equations, you're going to be putting numbers in, and you may have to keep playing with different numbers in order to make it work. So you may have come up with coefficients, for example, in front of CH4, maybe you have a 2 in front of O2, maybe this was a 4. In front of CO2, this would be a 2, and in front of the waters, you have a 4 as a coefficient. So those coefficients, if you went ahead and added all your atoms of each element, would be a balanced reaction. However, if you look at these coefficients, we have the ratio of 2 to 4 and 2 to 4. We can reduce that by dividing all of them by 2, and that would reduce it to what we originally determined with the 1, 2 on the left and the coefficients of 1 and 2 on the right. So that's what they mean when they say reduce to the lowest term if necessary. This slide shows us at the molecular level the balanced equation between methane, CH4, with 2 oxygens producing carbon dioxide and 2 water molecules. So again, CH4 were represented here. The white spheres represent our hydrogens, and we can see there's 4 hydrogens in that 1 molecule. On the right, in the 2 water molecules, again, the whites are our hydrogens. There's our 4 hydrogens. Our 2 molecules of oxygen are represented here. And then in our products, here's my 2 oxygens, those red spheres in the carbon dioxide and the red spheres in the water molecules. And then the black ball represents a carbon. So we have the 1 carbon in CH4 and the 1 carbon in CO2. Balance the following equation. Phosphorus solid plus chlorine gas produces phosphorus chloride liquid. Phosphorus is one of our polyatomic elements. So 1 molecule of phosphorus contains 4 atoms of phosphorus. Chlorine is one of our diatomic elements. So a molecule of chlorine contains 2 chlorine atoms. A molecule of phosphorus trichloride contains 1 phosphorus and 3 chlorines. So we can see that our reaction is not balanced because we have 4 phosphorus in our reactants and only 1 phosphorus in our product. So in order to balance that, we'll add a coefficient of 4 in front of phosphorus trichloride. So now we have 4 molecules of phosphorus trichloride, and that now gives us 4 phosphorus and 3 times 4, 12 chlorines. Now our phosphorus are balanced in the reactants and the products. So in order to balance our chlorine, we need to multiply by a coefficient of 6. So 6 times 2 will give me 12 chlorines. So now we have a balanced reaction. Balance the following equation. Solid aluminum plus bromine gas produces liquid aluminum bromide. In our reactants, we have 1 atom of aluminum and we have 2 atoms of bromine in 1 molecule of bromine because that's one of our diatomic elements. Aluminum bromide, our product, we have 2 aluminum atoms and 6 bromine atoms in that molecule. So in order to balance our reaction, we need to add a coefficient of 2 in front of the aluminum. So we now have 2 aluminums to balance aluminum on the reactant and the product side. And now we need a coefficient in front of our bromine molecule to balance 6 bromine. So we have 2 already. So if we put a 3 in front, we would have 3 times 2 gives me 6 bromine atoms. So our bromines are balanced on both sides. So now we have a balanced equation. Balance the following equation for the reaction between solid barium, liquid water, producing aqueous barium hydroxide and hydrogen gas. The bariums are already balanced. There's one in the reactant, one in the product. The hydrogen in water, there's 2 in the reactant, and in the product we have 2 hydrogens in barium hydroxide and 2 in hydrogen gas. So there's a total of 4 hydrogens in the product. So we put a coefficient of 2 in front of water, and let's see if our reaction is balanced. So in barium we have 1. In 2 molecules of water we have 2 times 2 for the hydrogens. We have 4 hydrogens, and then 2 oxygens for 2 molecules of water. And in the products we have a barium, and then a subscript outside of the parentheses means multiply by everything on the inside. So that means we have 2 oxygens and 2 hydrogens, because again this means 2 hydroxide ions. And then in hydrogen we have 2 atoms of hydrogen in 1 molecule. So checking to see if this is balanced, our bariums check out. We have 4 hydrogens on the left, and on the right we have 2 hydrogens plus 2 hydrogens. That equals 4 hydrogens. So they are balanced. And then 2 oxygens balance 2 oxygens. So this is a balanced reaction. Write a balanced equation for the decomposition of solid mercury 2 oxide to form liquid mercury and oxygen gas. Let's start by writing our reactant, which is solid mercury 2 oxide. And that is what is decomposing to form liquid mercury and oxygen gas. So those would be our products. Now we are given the name mercury 2 oxide. We need to write the formula. We know this is a type 2 ionic compound because we have the parentheses with the Roman numeral in for the charge on the metal. So mercury is given to you. The symbol is Hg. The Roman numeral 2 tells us it has a +2 charge. Oxide came from oxygen. It's in column 6, so it forms a -2 charge. So in order to create our compound, that's when we cross our charges. We rewrite the formula and we bring the superscripts down, so we get Hg2O2, and we can reduce those subscripts to HgO. So that is our reactant, and that's a solid. So we could write HgO solid. It's forming liquid mercury. So mercury, we just said, the element symbol is Hg, and oxygen gas. So remember again, oxygen is one of our diatomic elements, so it's O2, and physical state is gas. Now we need to see if our reaction is balanced. Our mercuries are balanced because we have 1 on each side. However, we only have 1 oxygen in the reactant in mercury 2 oxide, and we have 2 oxygens in our product of oxygen gas. So in order to balance that, let's put a coefficient of 2 in front of HgO. That tells us we have 2 mercuries and 2 oxygens. Now our mercury on the right that's alone, there's only 1, so we put a coefficient of 2, so now we have 2 mercuries. And our diatomic molecule of oxygen contains 2 oxygen atoms. So now we can check if everything's balanced. 2 mercuries balanced, 2 oxygens are balanced. So we have a balanced chemical reaction.